Good day, everyone. My name is Teo Yin Yin, and today we are going to look into the problem 7, which is on the 150 years of Urease. Moving on the history of this remarkable enzyme, which was spans over a century of scientific evolution, it began back in 1876 when Frederick first identified urease activity as a soluble enzyme. This was a critical step in understanding how biological catalysts operate outside of a living cell. However, in 1926, urease was first enzyme ever to be crystalline. This was achieved by James using jack bean. Why was this so important? At that time, the chemical nature of enzymes was a total mystery. By crystallizing it, Sumner provided the definitive proof that enzymes are proteins. This discovery was so fundamental to the field of biochemistry that Sumner was awarded the Nobel Prize in Chemistry in 1946. So, when we study urease today, we are not just looking at the chemical reaction, we are looking at the molecule that prove the fundamental nature of all enzymes. Now, let's look at the chemistry behind the magic. Urease play a vital role in the global nitrogen cycle. It acts as a high-speed catalyst for the reaction you see here, where it converts urea and water into carbon dioxide and ammonia. Without this enzyme, this reaction would take centuries. With it, it happens in milliseconds. If you look at the diagrams here, we can see that urease belongs to a class of enzyme that utilized by nickel active site. The mechanism involved the enzyme ability to trap the urea molecule between these two nickel centers. Now, let's look at the conditions required for urease to actually function. Scientifically, the active center of urease behaves as a diprotic acid, as you can see from the equilibrium constant. It exists in 3 states depending on the pH of the environment. We have pKa1 at 5.62 and pKa2 at 9.07. Crucially, only the intermediate form, the Hu minus, the first deprotonations of the urease, that will show the enzymatic activity. This tells us that urease is highly sensitive to its environment. It works best in a specific pH range, which is roughly between 6 and 9. This is significant when we consider it working in the stomach or in the soil. Furthermore, the reaction follows Michaelis-Menten kinetics, whereby the equation given here, it shows the 2 processes. First, the reversible binding of the urea to the enzyme to form the complex. And second, the irreversible catalytic step where the product of carbon dioxide and ammonia are released and the enzyme is regenerated. By understanding these constants and the K2 rate, we can mathematically predict exactly how fast the urease will work under different physiological conditions. We have seen the chemical equations, but how do we measure the actual performance of an enzyme? This is where Michaelis-Menten kinetics come in. This model is important for three main reasons. First, it allows us to account the enzymatic dynamics. It gives us a framework to describe the transition from free enzyme and substrate to the enzyme-substrate complex, and finally to the product. Secondly, it explains the kinetic rate enhancement. As I mentioned earlier, Urease is incredibly efficient. This mathematical model helps us to quantify that enhancement, showing us exactly how the enzyme lowers the activation energy to speed up the reaction. Finally, and perhaps most importantly for laboratory work, it explains how reaction rates depend on the concentration of both enzyme and the substrate. If you increase the amount of urea, the reaction goes faster, but only up to a certain point. Understanding this kinetic is what allows scientists to optimize industrial process and calculate the correct dosage for enzyme inhibitors in medical treatments. So it turns a qualitative observations into a precise, predictable science. Now, let's answer question 1. Using the steady state approximation, derive the dependence of the rate of enzymatic reaction on the total concentrations of urease, urea, and acid. Note the condition provided. The total concentration of urea is much greater than the total concentrations of urease. This is a standard assumption in Michaelis-Menten kinetics, ensuring that the substrate concentrations remain relatively constant during the initial stages of the reaction. The process follows a two-step mechanism. First, urease binds with urea to form an intermediate enzyme-substrate complex, denoted here as this one. This step is reversible, with a forward rate constant K1 and a reverse rate constant K-1. In the second step, the complex breaks down to release the product carbon dioxide and ammonia and regenerate the original enzyme urease. This is the catalytic step governed by the rate constant K2. The overall rate of the product formations or the rate or the reaction velocity is determined by this second step here. So dP dt equals to K2 multiply the concentrations of the complex. To solve for the rate, we need to find an expression for this intermediate complex. Since the intermediate complex is highly reactive and its concentration remains low and constant during the main part of the reaction, we apply steady state approximation. This means we set the rate of change of the complex concentrations to 0. The complex is formed by the forward reaction K1 and consumed by both the reverse reaction K-1 and the product formation 2, K2. By rearranging that equations, we can express the concentrations of the complex in terms of free enzyme and substrate. We often define the Michaelis constant Km as the inverse of this fraction here. Now that we have established the steady-state intermediate, we can express the initial rate of the product formation dP dt by substituting the intermediate complex expressions into our rate equation. We get this. However, in laboratory setting, we don't usually know the free concentrations of enzyme. or substrate at any given moment. We only know that we initially put into the beaker the total concentrations. First, we look at the substrate, urea. The total concentrations of urea is the sum of the free urea and the urea currently bound to enzyme. But remember our initial assumption. The total concentrations of the urea is very much higher compared to the concentrations of the enzyme. Because there is so much more substrate than enzyme, the amount of urea tied up in the complex is negligible. So we can neglect this one. Therefore, we can safely approximate that the total concentrations of the urea is approximate to the concentrations of the urea. This simplifies our max significantly as we move forward. Next, we must account for the fact that enzymes like urease are pH sensitive. The enzyme exists in different protonation states, but typically only one specific state is catalytically active. We represent this using the fraction alpha HU minus to represent the active enzyme, which accounts for the acid-base equilibrium of the enzyme. The total enzyme concentration is now distributed across all protonation states and the enzyme-substrate complex. We adjust our mass balance by dividing the enzyme term by this fractional ionization constant, alpha. By substituting our earlier expression for the intermediate complex into the mass balance equation, we arrive this relationship. Finally, we rearrange this to solve for the free urease, which is in these expressions here. This is a critical step because it allows us to replace the unknown free enzyme term in our original rate law with terms we can actually measure, which is the total enzyme, the total substrate, and the pH-dependent alpha value. In the previous step, we introduced a variable called alpha HU negative charge. But what exactly does it represent? In enzymatic reactions, the protein's shape and charge are determined by the pH of the environment. For urease, we assume that it exists in three states based on the number of protons attached, which are H2U with 2 protons, HU negative charge with 1 proton, and U2 doubly negative charge with no proton. Crucially, only HU minus or one single proton form is catalytically active. Therefore, alpha HU negative charge is defined as the fraction of total urease present in that specific active state. It tells us exactly what proportion of our enzyme is actually awake and ready to work. To calculate this fraction, we look at the two-step dissociation of the enzyme. The first dissociation constant, Ka1, governs the transition from the fully protonated H2U to our active HU negative charge. The second constant, Ka2, governs the transition from our HU negative charge to the deprotonated U2 negative charge. Mathematically, the fraction is the concentrations of the active form, HU minus, divided by the total of all possible forms. To make this useful, we need to express those concentrations in terms of proton concentrations and Ka constant. Using the equilibrium expression, we can substitute H2U becomes H, or the proton concentrations, multiply the concentrations of HU minus divided by Ka1, and the concentrations of U2 minus is substituted become Ka2 multiply the concentrations of Hu minus or negatively charged divided by the concentrations of the proton. When we plug this back into our fraction, the concentrations of the Hu negative charge term in the numerator and the denominator cancel out. This leaves us the final expression for the active fraction alpha equals to 1 over the expressions here. And this is a powerful result. Why? Because it shows that the enzyme's activity follow a bell-shaped curve when plotted against pH. If the concentrations of the proton is too high, the first term dominates and the enzyme is inhibited. If the concentrations of the proton is too low, the third term dominates. By substituting back this one into our rate law, we have successfully derived a complete model for Urease activity that accounts for the substrate concentrations, the total enzyme, and the specific pH of the system as shown in the next slide. By taking the initial rate equations as given here and substituting the expressions we derive for the free enzyme and the active fraction as shown in the previous slide, we get this comprehensive expression for the rate of product formation dP dt. At first glance, this looks very complex. However, through algebraic simplifications, specifically by multiplying the numerator and the denominator by the term k minus 1 plus k2, we can clean this up significantly. Notice how the rate constant k1, k minus 1, and k2 begin to group together. This allows us to see the familiar structure of Michaelis-Menten equation emerging from the max. So we have these equations and we substitute the concentrations of the Urease that we derived earlier. Similarly, we have to replace the alpha with what that was derived in the slide before, and that is the equations we get. We further simplified it through the multiplications of k minus 1 plus k2 into the fractions at the denominator, while we keep this part here remain the same. After that, we do some simplifications by divide the whole equations with k1 for top and bottom, and that is the final equations for the dP dt. This final result expresses the reaction rate in terms of variables we can control or measure in the lab, which are the total concentrations of the Urease, the total concentrations of the urea, and the hydrogen ion concentrations, H+. So the denominator now contains a term that looks very much like a Michaelis-Menten constant Km, but it is now modified by the pH-dependent term shown in the parentheses here. Now that we have the full comprehensive rate equation for Urease, we can use it to determine the reaction orders. The reaction order tells us how sensitive the rate is to changes in the concentrations of urease and urea. Let's look at a specific case where the buffer solution creates a very high mechanism constant relative to the substrate concentrations. In this scenario, we assume that this constant is much larger than the total concentrations of the urea. Mathematically, when one term in the sum is significantly larger than the other, the smaller term, in this case, urea total concentrations in the denominator becomes negligible and can be ignored. Once we remove that substrate term from the denominator, our equation simplifies. Look closely at the new structure. In a buffer solution, the pH is constant. So the entire denominator here, this part, just a constant value. Notice that both urease total concentrations and the urea total concentration are now in the numerator and are each raised to the power of 1. Because the rate is directly proportional to the concentration of each reactant, we can conclude that under these specific conditions, the reaction is first order with respect to urease. So N equals to 1. The reaction is also first order with respect to urea. So N is also equals to 1. This means that if you were to double the amount of enzyme, the reaction would go twice as fast. Similarly, because we are in the first order regime for the substrate, doubling the urea would also double the reaction rate. Now, let's consider the opposite extreme. What happens when the total concentration of urea is very high? In this case, the total concentrations of urea is much larger than the Michaelis constant term. This part. This represents a state of enzyme saturation, where practically every available active site on the urease molecules is occupied by the urea molecule. Because the total concentrations of the urea is so large, the first term in our denominator, the ratio of the rate constant, becomes negligible. As we simplify the max, notice something very interesting happened. We have a concentration term for urea in the numerator and a matching concentration term in the denominator. These two terms cancel each other out completely. Once those terms cancel out, our rate equation looks like this. Notice that the concentrations of urea is no longer part of the equation. In a buffer solution where pH is held constant, the entire denominator is just a fixed number. This tells us that adding more urea at this stage will not speed up the reaction any further. So based on this final expression, we can determine our reaction order. The reaction remains first order with respect to urease. So N equals to 1. If you add more enzyme, you provide more workstations, so the rate increases. However, the reaction is now zero order with respect to urea. So N equals to 0 for urea. And this is the hallmark of saturation kinetics. The enzyme is working at its maximum capacity, and the substrate concentration no longer limits the speed of the product formation. We have seen that the reaction rate of urease is highly dependent on pH, forming a distinct bell-shaped curve. But what exactly pH does the enzyme perform its best? We will calculate the specific pH value where urease demonstrates its maximum rate, given as R subscript max. Since we are holding the concentrations of urease and urea constant, the rate depends entirely on the variable of proton concentrations. To find the maximum of any curve, we use calculus. Specifically, the maximum rate occurs when the first derivative, dr, concentrations of proton, is equals to 0. Before we proceed to the differentiation, we represent the denominator with the symbol of U. So we have the R equals to the constant divided by U, which is this part of the expressions, followed by differentiations with respect to U. Therefore, dr du equals to negative constant multiply U to the power of minus 2. After that, we differentiate U with respect to the concentrations of proton, where we will get 1 over Ka for this part and Ka2 over concentrations of proton square for this part. Next, we use the chain rule, whereby dr dH concentrations equals to dr du multiply du to the concentrations of proton. So we cross multiply this and this one by substitute back the expressions for the U into the equations, followed by the simplifications. To obtain the maximum rate, we equal the derivative to 0, followed by some rearrangement. Then we get the relation between pH and pKa. And we substitute the pKa1 with 5.62 and pKa2 with 9.07 into the equations, then the respective pH to achieve maximum rate is 7.35. So it is the point where the enzyme is the most effective at breaking down the urea, providing a perfect balance between its protonated and deprotonated state.
Question 4. In the absence of any buffer, the decomposition products of urea change the pH of the solution, thereby reducing the activity of urease. Calculate A. The pH of the solution after decompositions of 0.005 molar urea and neglect the contribution of urease to the acid-base equilibrium and the dissolution of atmospheric carbon dioxide. We are given several key constants here: the pKb of ammonia, the pKa values for the two stages of carbonic acid, dissociations. Based on the reaction stoichiometric here, the decomposition of 0.005 molar for this urea use 0.005 molar of carbon dioxide and 0.01 molar ammonia. Notice the 1:2 ratio of carbon dioxide to ammonia. Once carbon dioxide and ammonia are released into the aqueous environment, they don't just sit there, they react. The most significant initial reaction is the formation of ammonium bicarbonate. We can determine the extent of this reaction by calculating its equilibrium constant K, where if we refer to the equations here, it is the product over the reactant. So by combining the expressions for the acid dissociation of carbon dioxide from this part, the base dissociations of ammonia from this part, and the auto-ionizations of water, we find that Ka multiply Kb over Kw is equals to the equilibrium constant. Plugging in our values for Ka, Kb and Kw, we get a K of approximately 3.16 times 10 to the power of 5. Because this constant is so large, we can assume this reaction goes virtually to completion. Since we have 0.005 molar carbon dioxide and 0.01 molar ammonia, the 0.005 of carbon dioxide will react completely with half of the available ammonia. This leaves us with a solution containing 0.005 molar bicarbonate, 0.005 molar ammonium, and a residue of 0.005 molar unreacted ammonia. Residual ammonia can react with bicarbonate to form carbonate as follows. Now we have to consider if that residual ammonia further react. It can react with the newly formed bicarbonate to produce carbonate and more ammonium. Again, let's look at the equilibrium constant for this second step. Using the second dissociation constant of carbonic acid, Ka2, we find the equilibrium constant equals to 8.32 times 10 to the power of minus 2. Unlike the first reaction, this K value is quite small. This tells us that the conversion to carbonate is minimal. The system will primarily exist as a mixture of bicarbonate and its conjugates, base or acid partner. So, where does that leave our pH? The solution now effectively functions as a mixture of two systems, but it is almost easily viewed as an ammonia-ammonium buffer. We have equal concentrations of ammonia and ammonium, both at 0.005 molar. While we previously estimated that the second reaction between bicarbonate and ammonia wouldn't shift the pH much, let's prove it with rigorous calculations. We will use initial, change, final, equilibrium to find the exact concentrations. We start with our initial concentrations of 0.005 molar for bicarbonate, ammonia, and ammonium. We assume a change of X as the reaction proceeds toward carbonate. This gives us our equilibrium expressions, which is 0.005 minus X for the reactants and 0.005 plus X for ammonium product. Now we set this up in our equilibrium expression. Because the constant K is small, which is 8.32 times 10 to the power of minus 2, we can make a simplifying assumption, which is X is much smaller than 0.005. This allows us to treat 0.005 plus minus x as approximately 0.005. With our simplification, the maths become much cleaner. The 0.005 term in the numerator and denominator cancel out, leaving us with a simple linear equation where x equals approximately 3.39 times 10 to the power of minus 4 molar. This x represents the concentrations of carbonate ion produced. Now we can use the second acid dissociation constant Ka2 to solve for the actual hydrogen ion that are present in the solutions. By rearranging the Ka2 formula, we plug in the known pKa of 10.33. Our calculated carbonate concentration for the denominator and our remaining bicarbonate concentration, which is 0.005 minus that small value of x in the numerator. So by solving this, gives us an concentration of hydrogen of 6.43 times 10 to the power of minus 10 molar. Finally, taking the negative log of that concentration gives us our refined pH, which is approximately 9.19. The decomposition of urea creates a highly alkaline environment, which is a critical factor in understanding the biochemical kinetics of the urease enzyme. Question 4b. The factor by which the rate of the enzymatic reaction decreases when the pH of the solution changes from neutral to the value obtained in equation 4a. If the total concentration of urease and urea are the same in both conditions. Now that we have established how much the pH shifts, we need to calculate the actual biological consequence. How much does this shift slow down the enzyme? The rate equation for urease is dependent on the concentrations of hydrogen ions. In the denominator, you will see a term involving Ka1 and Ka2. This represents the dissociation constant of the ionizable group in the enzyme's active site. For urease to function optimally, this group must be a specific protonation state. If we hold the enzyme and substrate concentrations constant, the rate becomes purely a function of concentrations for proton. At neutral pH of 7, we plug in our values and find that the rate is approximately 0.9522 times the constant. By substituting 10 to the power of minus 9.19 into our rate equation, the efficiency of the enzyme drops significantly to 0.4313 times the constant. When we compare the two conditions by taking the ratio of the rate at pH 7 to the rate at pH 9.19, we get a value of 2.12. This means that in an unbuffered solution, the accumulation of decomposition products changes the environment so drastically that the enzymatic reaction slows down by a factor of more than 2. This is clear quantitative look at product inhibition via environmental shift. Let's look at the big picture by matching 3 different experimental conditions to their corresponding phase figure of pH versus product concentration. For condition 1, urease in buffer solution with urea. In a buffer, the pH is designed to remain constant regardless of product formation. This matches figure C, where we see a flat horizontal line. For condition 2, urease in neutral solution with urea without any buffer. As we just calculated, the product of ammonia and carbon dioxide cause the pH to rise steadily as more product is formed. This is represented by figure A, showing a continuous upward curve that eventually level off. For condition 3, urease in liposome with a permeable membrane with urea and without any buffer inside. Assume that the urease doesn't leave the liposome, while urea and product can pass through the membrane. Here, the products are formed inside a small volume, raising the pH, but they also diffuse out across the membrane. This creates a cycle or a loop in the phase space as the system seeks equilibrium between production and diffusion. This complex behavior is shown in figure B. Question 6. Calculate the minimum concentration of calcium at which calcium carbonate begins to precipitate from solution in equation 4a. Ignore the dissolution of atmospheric carbon dioxide. Beyond just shifting pH, the decomposition of urea has exciting engineering application. One of the most promising is biocatalytic calcification. When the ammonia produced by urease raises the pH, it shifts the carbonate equilibrium to favor the formation of carbonate ions. In the presence of calcium ion, this leads to the precipitation of calcium carbonate. This process is being used to develop self-healing concrete, seal fissures in historical stone monuments, and even remove heavy metals like strontium-90 from wastewater. Our task here is to calculate exactly how much calcium is needed to trigger this precipitation, given the information of Ksp for calcium carbonate at 25 degrees C, as given here. To find the minimum concentration of calcium required, we use the solubility product constant Ksp. For calcium carbonate at 25 degrees Celsius, the solubility product constant Ksp is 3.36 times 10 to the power of minus 9. From our earlier refined calculation in question 4a, we know that the concentrations of carbonate ions in our solution is 3.39 times 10 to the power of minus 4 molar. By rearranging the Ksp expression, we find that precipitation begins when the calcium concentration exceeds the ratio of Ksp to the carbonate concentration. Plugging in the numbers gives us a threshold of 9.91 times 10 to the power of minus 6 molar. Essentially, if the calcium concentration is greater than 1 times 10 to the power of minus 5 molar, the solution becomes supersaturated and solid calcium carbonate will begin to form. Moving from the lab to the field, Urease plays a vital role in global agriculture. It breaks down urea-based fertilizer to provide plants with nitrogen in the form of ammonia. However, there is a catch. If the hydrolysis happens too quickly, the sudden surge in ammonia can lead to ammonia volatilization, where nitrogen is lost to the atmosphere and can even cause alkaline-induced damage to the delicate plant roots. To manage this, farmers use urease inhibitors. These compounds slow down the enzyme, ensuring a steady, manageable release of nitrogen that matches the plant uptake rate, protecting both the crop and the environment. This principle of inhibition isn't just for soil. It's also used in advanced analytical chemistry. For example, boric acid acts as a competitive inhibitor for urease. It mimics the substrate and binds to the active site, blocking urea from entering. This interaction is exploited in urease-based biosensor. By measuring how much the enzyme activity is suppressed, scientists can detect and quantify the presence of specific inhibitors or heavy metal in a sample. Whether we are sealing crack in an ancient building or monitoring environmental pollutants, the chemistry of urease proved to be a versatile tool in modern science. In question 7, we are going to rederive the dependence of the enzymatic reaction rate on 4 key factors: the total concentration of urease, the substrate urea, the competitive inhibitor boric acid, and the concentration of hydrogen ion. We make 2 simplifying assumptions to keep the max manageable. First, that the substrate and inhibitor are in much higher concentration than the enzyme. Second, we will ignore the acid-base properties of boric acid itself. We start with the fundamental rate of product formation, which depends on the equilibrium concentrations of enzyme-substrate complex. To solve this, we must use mass balance. Because urea and boric acid are in great excess, their free concentrations are effectively equal to their total concentrations. However, the enzyme urease exists in several forms: the free enzyme, the enzyme substrate complex, and the enzyme inhibitor complex. The active form of the enzyme is pH dependent, which is Hu-. We account for this using the term alpha Hu-, which represents the fraction of the enzyme in its active deprotonated state. By summing these forms and substituting the equilibrium constant for binding, which are including K1, K-1, and K2, and the equilibrium constant for inhibitions, Ki, we arrive at the total enzyme concentrations, expressions that includes all 3 states. Let's look closer at that alpha Hu- term. Since the enzyme is active site behave like a diprotic acid, it can be fully protonated, which has the H2U active, which is a Hu negative charge, or fully deprotonated, U with 2 negative charge. The fraction of the active form is defined by the concentrations of Hu-, which is this one, divided by the sum of all three states. By substituting the acid dissociation constant Ka1 and Ka2, we arrive a universal term that depends only on the pH of the solution. This is the mathematical heart of why enzyme rate drops when the solution becomes too acidic or too basic. Now we bring everything together. We substitute our expression for the free enzyme, which is the Urease, into the initial rate equation. From these expressions, substitute into the rate equation. After some algebraic heavy lifting, cancelling terms and grouping constant, we arrive at our final comprehensive rate law. Look at the denominator. It is now composed of three distinct factors. One represents the basic Michaelis-Menten kinetics. One represents the impact of the competitive inhibitor boric acid. And the final term represents the pH dependency. This single equation allows us to predict how the reaction will behave in real-world conditions where multiple environmental factors are shifting simultaneously. Question 8. According to the kinetic equation obtained, the function reciprocal rate equals to a function of reciprocal concentrations for the urea, which it will give a linear plot. Calculate Ki if the slope of this function with boric acid total concentrations equals to 0.3 millimolar is 2.48 times greater than the slope of boric acid total concentrations equals to 0.07 millimolar at 25 degrees Celsius. The concentrations of Urease and pH values are equal in both cases. To extract useful experimental data, we often transform our complex rate law into a linear form. By taking the reciprocal of our rate equation, we create a function of 1 over R versus 1 over concentrations of the urea, commonly known as Lineweaver-Burk plot. In this linearized equation, several terms simplify into familiar kinetic constant. The group of rate constant in this green box is defined as the Michaelis constant, which reflects the enzyme affinity for the substrate. Meanwhile, the numerator term in this box here, which is K2 multiply the concentrations of the Urease total, represent the maximum rate, the theoretical speed achieved when every enzyme molecules is saturated with substrate. When we look at the slope of this linear function, we see that it is indirectly influenced by the concentrations of inhibitor boric acid. Mathematically, the slope is defined as these expressions. This is the hallmark of competitive inhibitions. The inhibitors increase the effective Km, making the slope steeper, but it does not change the y-intercept 1 over R max. As you can see in the graph, increasing the boric acid concentrations from 0.075 millimolar to 0.3 millimolar significantly increase the slope of the line while rotating around the same point on the vertical axis. Finally, we can use the ratio of this slope to solve for Ki, the dissociation constant for enzyme inhibitor complex. We are told that the slope with 0.3 millimolar inhibitor is 2.48 times greater than the slope with 0.075 millimolar inhibitor. By setting up the ratio, the Km and Rmax terms cancel out because the enzyme concentration and the pH were held constant in both experiments. This leaves us with a single equation where Ki is the only unknown. Solving this expression reveals that Ki equals to 7.7 times 10 to the power of minus 5. This value gives us a precise quantitative measure of how tightly boric acid binds to urease, providing the data necessary to design effective agricultural inhibitors or highly sensitive biosensor. To conclude our study, we are moving from kinetics to thermodynamics. We want to calculate the standard enthalpy and entropy for the binding of boric acid to urease. It is important to note that the Ki we calculated previously is a dissociation constant of the complex. Thermodynamics calculations for a binding process require the association constant, which is K bind equals to 1 over Ki. Using our known Ki values at two different temperatures, 25 degrees Celsius and 35 degrees Celsius, we find that the binding constant decreases as temperature rises. At 298 Kelvin, K bind is roughly 12,987, but at 308.15 Kelvin, it drops to 6,369. This temperature dependence is the key to unlocking the energy profile of the reaction. To find the standard enthalpy of binding, we employ the Van Hoff equation. This equation relates the change in the equilibrium constant to the temperature. By plugging in our two binding constants and their respective temperature and using the ideal gas constant R, we can solve for the enthalpy change. The calculation yields a value of approximately negative 54.4 kJ per mole. Because the enthalpy is negative, we now know that the binding of boric acid to urease is an exothermic process. This explains why the binding constant decreases as we add heat to the system. The system will shift to oppose the temperature increase and favoring the dissociated state at higher temperatures. Finally, we determine the standard entropy, delta S. First, we calculate the standard Gibbs free energy, delta G, at 25 degrees Celsius using the relation as stated here. So this gives us a delta G equals to negative 23.5 kJ per mole. The negative value confirms that the binding is a spontaneous process under standard conditions. Now, we use the fundamental thermodynamic identity, which is stated here, for delta G equals to delta H minus temperature multiplied delta S. By substituting our value for G, H, and T, we solve for the entropy, which comes out to approximately negative 103.8 joule per mole per Kelvin. The negative entropy change makes physical sense. When the free inhibitor molecules bind to the enzyme, the system loses degree of freedom, becoming more ordered. However, because the exothermic enthalpy release is so large, it overcomes the entropic penalty, driving the formations of enzyme inhibitor complex. And that brings us to the end of our comprehensive analysis. From calculating pH shifts in a simple solution to deriving complex inhibited rate laws and determining thermodynamic constants, we have explored the intricate chemical life of Urease. Thank you.